Okay, what we're going to look at now are limits of algebraic expressions, or functions, if you will, that when you replace whatever x is approaching into every x in the function, you get a real defined answer. If that's true, unlike the previous two examples, unlike these, right? You couldn't just plug in -1 here and get a real defined answer. You couldn't just plug in 0 here and get a real and defined answer, right? So what if you do get a real defined answer? Well, the properties state that whatever you get is the answer to the limit. So very simple. If x approaches 4, plug in a 4 here for x. What is 8 times 4? Well, I believe that's 32 last time I checked. This is a nice real defined number, and that is the limit. That's the answer. What about letter B? What's the limit of the 4th root of x as x approaches 16? Well, is it possible to replace 16 into this x? Take the 4th root of it? Yes, it is. The answer is 2. And that's also the answer to the limit. All right, what about this one? The limit of this quadratic function as x approaches 2. Well, can you replace every x here with a 2 and simplify it and get a real defined answer? Well, sure you can. And I believe that's what? 2 squared is 4 plus 5 times 2. That's 10. That's 14. 14 and 4. That would be 18. 18 is your answer there. And what about this one? Can you again replace every single x in this expression, this rational expression, and get a real defined answer? Yes. We just did this one. That's 18 over what? 2 into this x. 2 plus 4 would be 6. So you get 18 over 6, 3. That quotient would be 3. And that's all you have to do for these types of limits. If you get something like this to come up, it's a gift. This is nice. Okay? All right, another type would be that of indeterminate form. So if we have a situation where we're looking at a limit of a rational function like this, and if you replace the 2 into every x, just like we did in the previous examples, you do not get a situation where you have a real defined answer. One thing we can do is factor first and reduce second. So do you see that if we plug in a 2 into this x specifically, in the denominator, you get 2 minus 2, which is 0. That's going to definitely give us an undefined situation, at least if not indeterminate. Okay, and it does end up being indeterminate because that you get a 0 over 0. So what we can do in these situations is, again, first factor and then see if we can reduce. So this numerator, x squared plus 2x minus 8, is factorable into these two binomial expressions. And so because it is factorable in that way, do you see you now have a factor repeating on both the top and the bottom? So we can cancel these out, and this gives us now the limit of x plus 4 as x approaches 2. Okay, so at this point, you have a situation where you now are able to replace this x with a 2 and get a real and defined answer. And that answer, that result is 6. And that is the limit. So the limit of this function as x approaches 2 is 6. Moving on to letter B. Similar situation here. If you replace every x with a 4, what do you get? Well, on the bottom, you get the square root of 4, which is 2. 2 minus 2 is 0. On top, 4 minus 4 is 0. Again, a 0 over 0 indeterminate form. So what we're going to do is see if we can factor this and reduce. This actually is factorable. This x minus 4 is a difference of 2 squares. It may not be that obvious, but it is. And the factorization would look like so. All right, do you agree if you were to FOIL, remember FOIL? If you were to FOIL these two binomials together, would you get this, x minus 4? And you would. So, because that's true, and because you have now the same factor on top as you do on the bottom, you can cancel those out, leaving you with just the limit of the square root of x plus 2, all, over 1, understood. As x approaches 4, make sure you put this notation in front every single time. LIM for limit, abbreviation for limit, and then as x approaches 4, okay? So as x approaches 4 here in this, all you got to do is substitution, then simplification. So square root of 4 is 2. 2 plus 2 is 4. The answer to this limit is 4. The final topic of discussion in section 9.1 would be limits of rational functions at infinity. So I'll let you look at this theorem and hopefully these 3 pieces of information will be very helpful to you in determining limits of rational functions at infinity. When I say at infinity, it could be in positive infinity or negative infinity. So let's review here these 3 scenarios. If the degree of the top is greater than the degree of the bottom, and x is approaching positive or negative infinity, then the answer is going to be infinity every single time. If the degree of the top is less than the degree of the bottom, the denominator, then the answer is going to be 0 every single time. If the degrees are the same, if the degree of the numerator is equal to the degree of the denominator, then the limit will be equal to the ratio of the leading coefficients of the top and the bottom. Let's see how this works. Letter A, find the limit of this rational function as x approaches infinity. Well, determine the degree of the top. The degree of the top, how do you do that? You look at the highest, greatest exponent that base x is raised to. And whatever that greatest exponent is, that's the degree of the expression. So in this case, the degree understood is 1. And now in the denominator, the degree is 2. So this is a situation in which the degree of the top is less than the degree of the bottom, and you're approaching plus or minus infinity. Therefore, the answer will be 0. Zero. Letter B. Again, determine the degree of the top and the degree of the bottom. They're the same in this case, correct? You got a 2 on top, you got a 2 on the bottom. The degrees are both 2. You're also approaching plus or minus infinity. So if the degrees are the same, what do we do? The answer is going to be the ratio of the leading coefficients of the top and the bottom. So what are the leading coefficients? Well, the leading coefficient of the top is understood to be 1. The leading coefficient of the bottom is understood to be, well, it's not understood, it's right in front of your face. It's 5. So the answer to this limit is 1/5. Okay. Our final example from section 9.1 is right here. The limit of this rational function as x approaches negative infinity. Well, look at the degrees, folks. Look at the degrees. The degree on the top now, 3, is greater than the degree on the bottom, 2. Because the degree of the top is greater than that of the denominator, the answer will be infinity. All right, infinity. Now, what this really implies is that the limit does not exist. Okay, so understand, if you get an infinite, it's called English. Okay, can we talk? Take a deep breath. Unique New York. Unique New York. Okay, I believe I'm ready now. If the result of a limit is infinity or negative infinity, that really implies the result does not exist. And we'll talk more about that during class. Hope you're doing well, staying safe. Until next time, take care. Bye-bye.